Hey everybody, welcome to Unit 15. Um, this unit will talk about buffers and titrations a bit. This is a follow-up to Unit 14, which is on acids and bases. So a lot of what we're doing is very related. We're just adding some new sort of a twist to it. Let's go ahead and get started. All right, we're going to start talking about what we call the common ion effect. And this is going to talk about some math, which you're going to have to use to learn more about buffers. So consider a solution with a weak acid. So we'll use hydrofluoric acid. We like that one a lot because it's just very simple, two elements. And it's in solution with a salt containing its conjugate base. The conjugate base of HF is just F minus. So I have these two reactions here. I have some NaF. The Na is pretty useless. It doesn't do anything in this reaction, but the F is what we're really paying attention to. And then over here I have HF makes H plus and F minus. We call it the common ion effect because both of these things, when they dissociate, make an F minus. We do not assume that the concentration of F minus is zero when we do an acid or base problem, as we had in the previous chapters. So basically what this is going to come down to is doing an ice table. All the ones in the last unit, you had zero of both of your products. Now we're going to see how that changes if you have some product to start off with and some reactant. How equilibrium changes as a result of that. This is called the common ion effect when a salt is added to a solution containing an ion in common with the acidic solution. In this case, the F minus is the common ion. Now, think about we're adding F minus to our equilibrium reaction here. Thinking a little bit back to equilibrium chapter, if I add F minus, it's going to shift the equilibrium in accordance to Le Chatelier's principle. Le Chatelier's principle says if I add F minus, the system's going to try to neutralize that change by shifting the reaction to the left to try to reduce the amount of F minus being added to the system. So the common ion effect is actually going to shift the equilibrium more to the left. Having a little bit of starting F minus in your reaction will actually make it so the reaction doesn't go as far to the right as it would with a basic acid and base reaction. What that kind of means is H plus, the thing we're looking for to measure pH, is there's less of this being produced. There's still some, but the common ion effect we're going to see is going to cause fewer H plus ions to be in solution, which increases the pH. Let's do an example here. We're looking at the H plus concentration and the pH of an HF solution. So that one example we're just talking about. This time it's going to contain our starting materials, 1 molar hydrofluoric acid, HF, and 1 molar NaF. NaF is a salt. It's not an acid or base by itself, although it might be acidic or basic. It's not acting as an acid or base because it doesn't have an H to gain or lose, but it will influence our pH in a different way. All right. So I have 1.0 molar hydrofluoric acid. That's the main thing doing everything here. It is our acid. Hydrofluoric acid will react in equilibrium with a hydrogen ion and a fluorine ion. Acids are proton donators, so this HF is going to lose its proton and be left with the anion F minus as the conjugate base. This is in equilibrium because HF is a weak acid. My other thing I have here is I also have a 1.0 molar NaF. When this is added to water, this is a salt, which will split apart into the Na plus ion and the F minus ion. Doesn't matter how much Na plus ion I have, it's not going to react with anything in any substantial way, so we don't really care about this. What's important is this F minus ion. If you look, I have F minus in my reaction of my acid here. So I have 1 molar NaF. When it splits apart, it'll make 1 molar F minus. So we're going to go ahead and set up an ice table. Our goal here is to find H plus. I want to see at equilibrium, once this reaction comes to an end, but once this reaction stabilizes, how much H plus I have left over. My starting information, I have 1 molar HF. I don't have any H plus to start with, but this time, unlike last time, I have some F minus to start because I also have 1 molar F minus in my solution. This is a little bit different than last time because we have something here. But let's think about which way this reaction will proceed. I still have 0 of this. So at the beginning, no reaction is going to the left because I don't have any H plus to start that reaction with. So the overall reaction will still go to the right, but we're not exactly sure how much. That just means I'm going to subtract X from this side and add X to both of these sides. Right, if I tried to subtract X from 0, I would have a negative amount of H plus, which is not good. My equilibrium concentrations, I'm just going to subtract them down. 1.0 minus X. I'm going to add down X, and this is 1.0 plus X. So X is going to be the sum amount that changed during this reaction. If we can solve for X, we're going to get what the unit we really want, which is this X. The equilibrium concentration of H+, that's the first thing we're trying to find in the problem, and we can use that to find pH. The way we're going to do that is by doing an equilibrium problem. It told me in the problem Ka is equal to 7.2 times 10 to the minus 4. That's equal to products over reactants, so it's H plus F minus over HF. I'm going to plug in, remember this is a K, so I have to plug in the equilibrium terms into this expression. So H is just X, F is 1 plus X, over HF is 1 minus X. We can solve this for X and get an exact answer, but it would involve using the quadratic formula and stuff. So what we're going to do is the same approximation, the same assumption we've been making. X is going to be a really small number. This reaction is only going to go a very little bit to the right because K is a really small number, and because Le Chatelier's principle is also pushing against it to the left. What that means is this 1 plus X term and this 1 minus term, 1 minus X term, both of those are just essentially just going to be 1. Plus X is going to be such a small number, it might end up as like something like 1.005, which for our purposes, it's close enough just to assume it is 1. So what we're going to do is simplify this a bit. Got to keep this X. Got to keep this 1, but I can get rid of the plus X. Over 1, get rid of the minus X. So all of this just means this is literally X. All these 1s just kind of go away. And I solve for X. This is our first answer. This is our hydrogen concentration, or H plus ion concentration. That's the first thing they're looking for in the question. And the second thing is just pH, which from last unit we know, pH is the negative logarithm of the H plus concentration. So I just plug in X, this number, into this formula. pH is about 3.14. If you did this exact same problem, let me pull it all up. You did this exact same problem, but you didn't have any initial common ion, F, to start, you'll notice X would be a slightly larger number, and the pH would be lower, more acidic as a result of that. The common ion effect can slightly affect the acidity of a solution. All right, today is very, we're going to start on that, very example heavy, very few slides, but a lot of showing our work. All right, that leads us into a buffered solution. A buffered solution is a solution that resists a change in pH when you add H plus, or acid, or O minus, which is like a base. When you add an acid or a base to a buffer, the pH changes a little bit, but only a little, not nearly as much as you would expect if the solution was not buffered. A buffer is made out of a weak acid and its matching salt, like we just did. HF and NaF is a buffer solution, or a weak base and its salt, like NH3 and NH4Cl. You have a conjugate acid-base pair, basically. You have a salt, and you have the acid, and they have the common ion that matches, that makes a buffer solution. Now, there's all sorts of math we're going to do with buffer solutions. We have a new formula to learn in just a minute, but this first example is going to be basically what we just did. We're starting, we have a buffered solution contains 0.5 molar acetic acid. Acetic acid is one you should probably know. We use this one a lot. It's made from the acetate ion gaining an H. So I have HC2H3O2. Its Ka is a number that might be getting familiar at this point, 1.8 times 10 to the minus 5. I also have 0.5 molar sodium acetate, which is NaC2H3O2. You see they both share a common ion. They both have the acetate, C2H3O2. So acetic acid is the acid, nacho there is the conjugate base pair that matches. And I want to find the pH of the solution. This is basically going to look like what we just did. So I have my acetic acid at 0.5 molar HC2H3O2, and I have 0.5 molar sodium acetate. Now the sodium acetate, again, is a salt. It'll split into this Na+, which won't react with water, it won't do anything that we need. And, more importantly, this acetate. So this 0.5 molar sodium acetate, we're really only interested in for the acetate component of it. All right, here we have our weak acid. This is what's going to dissociate. So we have our HC2H3O2. That's going to split apart in equilibrium because it's a weak acid. It's going to donate its proton, and the remainder is that acetate ion. Right, just like last time, I'm going to have an initial concentration of my acid, which is this 0.5 molar. I don't have any H plus to start, and this C2H3O2 minus, I have 0.5 molar. Okay, this is set up basically exactly like the last problem. I want to find the pH again, which means I need to know how much H plus I have at equilibrium. If I solve for that, I'll get the answer. So just like last time, I'm going to subtract from this side and add X to this side. This side is where I have to add because I have 0 H plus to start. So this reaction is going to proceed to the, this way, to the right. So I'm going to subtract my X, pull down X, 0.50 plus X. Those are my equilibrium concentrations. My Ka this time for acetic acid is given to me 1.8 times 10 to the minus 5. That's products over reactants, so it's going to be X 0.50 plus X over 0.50 minus X. Well, just like last time, let's do that shortcut. Let's get rid of this plus X and this minus X because X is going to be a really small number. So at the top here, I have 0.5 plus X. Let's get rid of that and just make it 0.5. Bottom, let's just make it 0.5 as well. Those 0.5s cancel, and X equals 1.8 times 10 to the minus 5. Move it up in just a second. Okay. We solve for X, and now we just take the pH because X is our H plus concentration. Okay, so again, just like last problem, pH is negative log of H plus concentration. So I'm going to take the pH of this number. And pH is equal to 4.74. So this isn't very different from what we did before. I'll show you the whole problem here. This is essentially solving a weak acid problem. It actually makes it slightly easier because you're able to get rid of this plus X because it's negligible. pH of this system, this buffer, would be 4.74 with these conditions. But we don't have to do all that work, actually. There's a shortcut formula we can use called the Henderson-Hasselbalch equation. It's a pretty easy equation to calculate the pH of a buffer. It's called the Henderson-Hasselbalch equation. So write this down. It is pH equals pKa. Okay, we haven't talked about pKa quite yet. We talked about Ka, though. Ka is the acid dissociation constant. It's products over reactants, your equilibrium for an acid. Now, pKa, it's just like pH. The P just means negative log. Okay? So pKa, actually what this P means, you'll take the negative log of the Ka, whatever it happens to be, plus the logarithm of this A minus, which is going to be our conjugate base. So in the last example, it would be our acetate ion, the thing on the right side of the equation, divided by our concentration of weak acid, the acetic acid. or whatever other acid we happen to be using. This formula will save us a lot of time. Here are the numbers plugged in from the last example. So you can solve pH equals, the P in pKa stands for negative log, and here you plugged in the Ka from that last example, 1.8 times 10 to the minus 5. Plus the log, you're going to put in your concentration of your anion, of your the salt, the ion that you have in common, on top, divided by the concentration of your weak acid. In the last example, both of these were just 0.5. Okay. To simplify this, we're going to do this example a couple times, but basically, this number here on the left, when you plug it into your calculator, is 4.74. This term, this log of 0.5 over 0.5, 0.5 divided by 0.5 is just 1, and the log of 1 is 0. So this ends up being 4.74 plus 0 equals 4.74. The same answer we got on our work last time, 4.74. So you can solve a buffer problem without doing all this work if we use the Henderson-Hasselbalch equation correctly. Here we have 3 examples to practice this. We're using the same buffer system, acetic acid, and our sodium acetate. Different concentrations, and we're going to find the pH of each of them easily. So I'm going to do the first one here. I'm going to solve the formula. pH equals pKa plus the log of the anion over the weak acid. Okay. In our problem here, the 0.5 molar NaCHO, this is our salt. So that's actually where we're going to plug here onto the end of the A minus. The HACE is a symbol for weak acid, which is the one that has an H in the front, like this one. So the acetic acid number is where we're going to plug in on the bottom. Okay. So for number 1 here, pH equals pKa. P stands for negative log. Ka, I don't have it on this slide, but we just said it was 1.8 times 10 to the minus 5 plus the log. Sorry, just checking my work. Plus the log of A minus, which is going to be the 0.5 molar, divided by 0.25 molars, the concentration of our weak acid. So, this number I just plugged into my calculator. Negative log of this is 4.74. Plus the log, we're going to plug this into our calculator. This is going to be the log of 0.5 divided by 0.25 is 2. Okay. So I'm going to plug log of 2 into my calculator and see what decimal that turns out to be. Nothing you'll have to do in your head here. So log of 2 is just a decimal. It's going to be 0.301. I'm going to add up these numbers together. 4.74 plus 0.301 is 5.04. That's the pH of my buffer. Just by solving this formula, I don't have to do my ice table, don't have to do my Ka and solve my equilibrium and all that stuff. Number 2, right? I just have slightly different values. Everything else stays the same. I'm going to write down the Henderson-Hasselbalch equation. pKa is the negative log of this number. I'm just going to go ahead and plug in the whole number here because I already know what it equals. Plus the log of, this time I have A minus is going to be 0.5 still, because that's how much my salt, NaCHO, I have. But this time my acetic acid, I have more, 0.75. Okay, so I have my 4.74 plus the log of, I'm going to take 0.5, divide by 0.75. Okay, that equals 2/3. Then I'm going to take the log of that, and I get a negative 0.176. My pH, when I add these two numbers together, comes out to 4.56. Okay, so let's kind of analyze these two, see what we have going on. In number 1, the one we had more of was the salt. Right? the anion, the C2H3O2, the conjugate base. All those are same words for it. I had more conjugate base, and that affected the pH by increasing the pH. It went from 4.74 if they were equal to each other to being 5.04. Now, number 2, I had more of the acid, which made this log value negative, which actually decreased the pH. So having slightly more acid in your buffer will make the pH a little bit lower. Having slightly more base will make it a little bit higher. Okay, now here in this last one, I have an equal amount of the two. So my pH is 4.74 plus the log of 0.005 divided by 0.005. Well, that's just going to equal 1. 0.005 divided by 0.005 equals 1. The log of 1 is 0. So if you have an equal concentration, your pH stays the same. If you have more base, the pH will go up slightly. If you have more acid, the pH will go down slightly. Okay. When acid or base is added to the buffer, do stoichiometry calculations first. In this section, what we're going to do, a buffer system, the purpose of it existing is it helps us neutralize pHs. When you can add a strong acid or strong base to a buffer, the pH doesn't change by as much as you would expect. If you add a strong acid to a buffer, it's going to react with some of the base, the conjugate base you have chilling in the buffer. It'll neutralize some of that. If you add a strong base to a buffer, it's going to react with some of the weak acid. Your buffer is able to neutralize a good amount of acid, and the pH will change, but only slightly. In this next couple of problems, we're going to talk about how adding a strong acid or strong base to your buffer changes the pH and how we can calculate that. These are some long problems. There's kind of a lot of work to go into it. We're going to do our best to keep it as organized as we can. So there's going to be the first part of the problem. We have to do a little bit of a stoichiometry calculation. When you add a base to an acid, it's going to neutralize it, or vice versa. After we do our little bit of stoichiometry, then we can do an equilibrium problem about it. So here is our long example. A lot to kind of go through here. It says calculate the change in pH that occurs when you have 0.01 moles of NaOH. Okay, that's our strong base. So identify 0.01 mole of NaOH, my strong base. Okay, I'm going to add that to 1 liter of a buffered solution from the previous example. So my buffered example is when I add 0.50 molar acetic acid, which was my HC2H3O2, and 0.50 molar of my sodium acetate, NaC2H3O2. Okay, so just to get us back where we were, we made a buffer out of my weak acid and its conjugate base. We're going to add a little bit of our sodium hydroxide, our strong base. This strong base is going to react with some of my weak acid, and they're going to neutralize each other. So let's show what that reaction looks like first of all. Okay, I have my acetic acid, HC2H3O2. This is my acid. So when I add base to it, these are the things that are going to react. Now it's going to react with NaOH. I don't care about the Na again. It's not really a part of this, so you can write it if you want, but I'm just going to write OH minus, because that's really all we care about with this term. This will be a regular reaction. This is a neutralization. It will occur to completion. Now I'm going to add that, and when these two things react, this is a proton donator. It's going to lose an H+. This is our base, a proton acceptor, so it'll gain that H+. So my H+ joins with my OH- to make H2O. The rest of this, the C2H3O2- is left. Okay, so this isn't an equilibrium, so we're not making an ice table yet, but what I want to see is how much of this I have left over. I want to see how adding this OH- affects my concentrations of acid and conjugate base. So let's put our starting conditions. I'm going to put our before we do any reaction. We said we have 0.5 molar of this. To keep everything in the same units, I'm going to turn everything into moles. Fortunately, in this problem, I have 1 liter of solution, which means molarity equals the number of moles. Because molarity is moles per liter, but if it's just 1 liter, molarity is the same as moles. So I'm going to say I have 0.50 moles of acetic acid from the 0.5 molar. OH minus is right here. I have 0.01 moles that I'm adding to my solution. H2O, no one cares. But acetic acid actually matters now. I started with 0.50 moles of acetic acid from my nacho. All right, a reaction is going to occur now. And let's think about what reaction happens. I have over here a little bit of acid and a little bit of base. So they're going to react with each other and neutralize until one of them runs out. Well, I have much less OH this time, so it's going to neutralize until it runs out. So my 0.5 moles of acid are going to neutralize 0.01 moles of base. So I'm going to lose 0.01 moles of OH minus. They're going to produce over here, though, 0.01 moles of my product, of my acetate ion. So this kind of looks like an ice table, but this is just what's happening in my reaction. I'm losing 0.01 moles of both of these because they're being neutralized, and I'm gaining 0.01 moles of acetic acid. I'm going to put my after step here, what I'm left with. I only end up with 0.49 moles of acetic acid. All of this is gone, and I have 0.51 moles of acetate. So adding 0.01 moles of strong base, all it did was neutralize just a little bit of this acid and make just a little bit more base. Even though this is a weak acid, it still reacts at a 1-to-1 ratio with this strong base. Okay. So these are my new concentrations of everything. So I'm just going to do the Henderson-Hasselbalch equation to see what my new pH is. My pH before, if I look at the last example, was 4.74. When I add this strong base, I would expect this to increase a bit because I'm adding base to it. If this wasn't a buffer solution, it would increase substantially. 0.01 mole of NaOH has a pH of like 12. So I'd expect this number to go up quite a bit. But if we actually solve it out, plus the log of base over acid of 0.51 over 0.49. Remember this pKa was 4.74 when we solved it, plus this log of those numbers. I got one moment. Take the log of that. I got just 0.0174. Add those two together, it hardly changes at all. My new pH is 4.76. I add a bunch of, or not a bunch, I add a little bit of strong base. I'd expect the pH to increase considerably, but because of my buffer system, it neutralizes that change. My pH only goes up. It does go up, but just a smidge, 0.02, which is like nothing. So that's the point of a buffer system. Buffer systems exist in our bodies to help our blood and our proteins stay at the correct pH, or otherwise we wouldn't be able to survive. We use buffer systems in science all the time because some reactions only occur at certain pHs. So it's really kind of an important concept. I worked it out with the Henderson-Hasselbalch equation. Alternatively, you could have done an ice table and everything like that. You would have gotten the same answer. I think it saves time to do the Henderson-Hasselbalch, and I think it makes sense to not have to do all of those assumptions in math again. Okay, we're going to compare this to the change that would occur in pH if you just added that NaOH to pure water. If I didn't add this to a buffer system, if I just added this to water, what would happen to my pH then? So if I have NaOH and I add it just to pure water, NaOH splits apart. It is a strong base into Na plus and OH minus. When you add it in water, it splits apart. Well, I had 0.01 molar NaOH, which means I make 0.01 molar OH minus. Well, I could take the pOH of that, because this is a strong base. It's the negative log of 0.01. The pOH is 2, which means the pH is 12. Pure water has a pH of 7. So when I added just this little bit of acid to my pure water, the pH went up 5 whole points. When I added it to my buffer solution, it only went 0.02 points up. So that's the difference that a buffer makes. Okay, next solution, we have one more buffer example here. A weak acid buffer reacts with strong acid. So calculate the change in pH that occurs when 0.20 moles of gaseous HCl. The fact that it's a gas doesn't really matter, but it's hydrochloric acid. It is a strong acid. I'm going to add it to that same buffer and see what happens. I'm adding an acid, so I'm expecting the pH to decrease. I'm expecting it to decrease a lot, except I know that this is a buffer, so it'll only decrease a little. It's added to 1 liter of the same buffered solution from that original problem. So let's set up our work here. Okay. Next problem, we have that same buffer. We have our 0.5 molar acetic acid. We have our 0.5 molar sodium acetate, or really all we care about is the acetate part. And I'm going to add, what did it say? 0.2 mole of a strong acid HCl. This one, I'm going to see what it reacts with. Hydrochloric acid is an acid, so this time it's not going to react with this other acid. That doesn't make sense. It's going to react with its conjugate base. The HCl is going to react with the acetate. That's part of the strength of a buffer system, is that it has something to react with bases, and it has something to react with acids. It can handle an increase of acid or base and neutralize it. So this time when a reaction happens, I'm going to write my reaction. I'm going to start with the acetate, because that is my base reacting with my hydrochloric acid. When these react, this is a base. It's going to gain an H plus and make my acetic acid back again. I gained an H, and I lost the minus charge because I gained a plus. Plus, this is going to just be a Cl minus, which that doesn't affect anything. That's the conjugate base of a strong acid. It doesn't react with water. It doesn't matter. So I'm going to look at my concentrations before my reaction. I have 0.50 molar of this. I have 0.50 molar of this. And I'm going to remember molar and mole mean the same thing because I have a 1 liter solution. I have 0.2 moles of HCl. That's a good amount of HCl. That's almost as much as these are. That's how much I'm starting with. So we're going to see what adding a whole bunch of HCl does to our buffer. All right, these two things are going to react with each other until they run out. HCl is going to run out first because you have less of it. So all of this is going to be used up. And I'm going to take it away from my base here. They're going to neutralize. But I'm going to make more of my acetic acid when they react. So after my stoichiometry, my new concentrations are 0.3 moles of acetate, 0 HCl left because it all got neutralized, and 0.7 moles of acetic acid. Okay, so I have 0.30 molar acetic acid, 0.70 molar acetate of both. I'm going to solve the Henderson-Hasselbalch equation to see how that affected my pH. It's going to be 4.74 plus the log. Be careful where I put my numbers. It's always the base over the acid. So I'm going to put the 0.3 on top. The acid on bottom, 0.7. Plug the log of 0.3 over 0.7 into my calculator. and that is a negative number, 0.368. My pH is 4.37. I added a considerable amount of hydrochloric acid, and still my pH hardly changed. Okay. All right, last, we're going to do one more example of a weak base buffer. So this buffer works pretty much the same, but there's going to be another formula we need to learn. So the pH of a buffered solution containing, this time I have, get my numbers, my 0.25 molar NH3, our favorite weak base, ammonia, and I have 0.40 molar NH4Cl. NH4Cl is a salt. It's going to split apart into its ions. Cl minus doesn't matter. We're looking at this NH4. So we're 0.40 molar NH4 plus. That's what I care about that salt. All right, this is a buffer solution because I have a conjugate acid-base pair in solution together. Let's find the pH of this. My reaction here, I have NH3 in equilibrium with, it's a base, it's going to gain a proton to make NH4 plus, and OH minus is my other product. Remember, this makes more sense if we think that this is the same reaction. What's really going on here is I'm adding this to water. Okay, and when I add this to water, the H plus part of water goes to the NH3, and then you're left with like an OH minus kind of left over. And that's where all these numbers come from. The H comes from a water molecule, so does the plus, and you're left with an OH minus kind of left over. But we usually write it like this, just because it's going to make their math look a little bit better. Right, my concentrations of everything here. This is a common ion problem. I have 0.25 molar NH3. I have 0.4 molar NH4. OH minus is what I'm looking for. I can find the pH or the POH and eventually the pH if I know the equilibrium concentration of OH minus. But I have 0 of it to start, which means this way will be minus X, this way gets plus X, 0.25 minus X, 0.40 plus X, and X are our concentrations. If I solve for X, I'll get my OH minus concentration, then I can find pH. The other information given to you is the Kb of ammonia. It is 1.8 times 10 to the minus 5. That equals products over reactants. My first product, I have 0.4 plus X at equilibrium. OH minus, I have just X. And last, I have 0.25 minus X. I'm going to use the same approximation to get rid of this plus X, get rid of this minus X, and instead, I'm just left with this expression here. Solve for this X, and I'll get the answer. When I do that math, I get 1.125 times 10 to the minus 5 equals X, which is my concentration of OH minus, because that's what X equals here. Use that to find POH. It's the negative log of this number. POH is 4.95, meaning my pH, if we remember, pH plus POH equals 14. 4.95 plus POH equals 14. I did that wrong. Okay, sorry. I know the POH, so pH plus 4.95 equals 14. pH equals 9.05. This is a buffer made out of a base, therefore it's slightly basic. If all that seemed like a lot of work after the last problems, it's because we didn't yet know the Henderson-Hasselbalch equation for bases. I can find the POH of a base using this version of the Henderson-Hasselbalch equation. POH is equal to the pKb, which makes sense because we're looking at POH, so Kb makes sense. It'll be the negative log of the Kb value plus the logarithm. This time, it's going to be our BH plus over our B. Okay, our BH plus, if we look at the previous problem, we had something, they're related to each other, except the NH4 has a plus and an extra H. So the BH plus is our acid that's made, our conjugate acid. The B is our starting base. Okay. So in this last example, BH plus would be the NH4 plus, and B would be NH3. So the B is the base before it gains a proton, and then the BH plus is the base after it gains a proton, the conjugate acid. They got the same answer as me, slightly different for rounding is all. pOH is 4.74 if you take the negative log of Kb. The log of the base, 0.4 over 0.25, equals about 9.06. So you can use both Henderson-Hasselbalch equations. The first one works for acidic buffers, and you'll need the pKa for that. And this one works for basic buffers, which you need the pKb for. All right. Buffered solutions contain relatively large concentrations of weak acid and corresponding weak base. They can involve a weak acid, HA. HA is the general form of any weak acid, and its conjugate base, A minus, or a weak base, B, and its conjugate acid, BH plus. When H plus is added to a buffer solution, when you add an acid, it reacts with the weak base. When OH minus, when a base is added to a buffered solution, it reacts with the weak acid. Okay? So there's the acids in the buffer can react with bases that get added, and vice versa. The pH in the buffered solution is determined by the ratio of the concentrations of weak acid and weak base. As long as this ratio remains constant, the pH will also remain constant. This will be the case as long as the concentrations of the buffing room materials are large compared to the amount of H and OH added. Buffers will work until you add too much strong acid or strong base. Once you use up all the buffer, the pH is going to start to change like normal. It'll change drastically. Okay. The buffer capacity is basically a measure of how much acid and base my buffer can absorb. The amount of protons or hydroxide ions the buffer can absorb without a significant change in pH. Usually if the pH changes by more than 1 pH point, so if it goes from like 4 to 3, or from like 2 to 3 or something like that, then we'd say the buffer is past its capacity. It's determined by the amount of weak acid and conjugate base, or base and conjugate acid. A buffer with a large capacity contains large concentrations of the buffering components. So here's an example. I have two different buffers. I'm going to calculate the change in pH that occurs when 0.01 mole of gaseous hydrochloric acid, so I'm adding more HCl, to 1 liter of each of the following solutions. Solution A is a buffer made of acetic acid and acetate ion, but I have 5 molar of each one. So I have a large concentration of weak acid and conjugate base. Solution B, I have the same sort of solution, right? I have 0.05 molar acetic acid, 0.05 molar acetate ion, but I have less concentrations of each one. And then I have the Ka of acetic acid to help. So I want to see what's the pH after this reaction. We already learned, so I'm not going to go through all the work again. We just did in the last example. We said the pH of this buffer before anything is added is 4.74. And that's true for both of these because the concentrations of acid and conjugate base are equal. So it's going to be 4.74 plus the log of some numbers that cancel out. So both A and B have a pH to start of 4.74. I'm going to add an acid to each of those, which is going to get rid of some of the things in my buffer, and I'm going to see what the new pH is for each of these. All right, so let's do our stoichiometry part of the problem. When I add acid, I have acetic acid, I have acetate, I am adding 0.01 moles of hydrochloric acid. When I add this hydrochloric acid, it is an acid, this is a minus, so it'll react with this base. So that's what our first reaction will look like. C2H3O2 minus plus hydrochloric acid yields, these are going to neutralize. This is my base, it's going to gain an H plus to make acetic acid again. and some Cl minus that we don't care about. Right, so before my reaction, with part A, we had 5 molar of this, so 5 moles of this. We had 0.01 moles of this. We have full 5 moles of this. So our HCl is kind of insignificant compared to our amounts of acid and base here. When the reaction happens, this strong acid is going to react with this weak base completely. All 0.01 moles of it will react with this until it's all gone. But I'm going to make 0.01 moles of my weak acid over here when that happens. So this is going to be 4.99 moles of this left over, no hydrochloric acid left over, and 5.01 moles of this left over. Let's plug it into the Henderson-Hasselbalch equation and see what our new pH is. It's going to be base over acid, so it's going to be the 4.99 over 5.01. Okay, this ratio gives me super small number, like 0.002. And when I add them all together, I get 4.738 as my new pH. My pH hardly changed at all from my original pH. Went down 0.002. Because I had a large concentrations of solution A and of my acid and my base, it did a really good job at neutralizing that pH. Now let's do it with B, where I have less. I have the same reaction going down. C2H3O2 minus reacting with my hydrochloric acid, the same amount of acid. For reaction after. This time, though, I only started with 0.05 moles of each of these, which means my 0.01 moles of acid seems more significant. All of it's going to react away, reducing this number by 20% and increasing this number by the same. I'm this time left with 0.04 moles of my acetate ion. No HCl is left over. 0.06 moles of acetic acid are left. When I solve for pH, the log of base over acid this time is a little bit more of a difference. It's going to be the log of like 2/3. When you add all this out, the pH drops significantly more than last time. Not a ton still, because we still have a buffer, but you notice the pH dropped a lot more. Having a higher concentration of your buffer leads to lower changes in pH. Okay, a couple things before we do another set of math problems. Large changes in the ratio of A- and HA will produce large changes in pH, which is not good. So you're trying to keep that ratio relatively consistent. Optimal buffering occurs when you have the same amount of each, when your concentration of acid equals your concentration of your conjugate base. The pKa of the weak acid to be used in the buffer should be as close as possible to the desired pH. So when you're making a buffer solution, you usually have a pH range you want to keep it around. Like this buffer we've been doing, that's 4.74 is kind of its default pH. It would be really bad if I wanted to keep my pH at 9, right? I'd have to break my buffer to get there. This would be really good at things in a pH range of like 4 to 5, because that's about where I want to keep my pH. If we want our buffered solution to be a pH of exactly 4, then the pKa of the acid we choose should be around 4 as well. All right, that's it for buffers for now. There's a lot there. We're going to practice those a bunch in class. Now on to our last little bit here is titrations. Okay. There is one more big math problem and then just a couple concepts to talk about. Very related to the common ion effect and stuff though, and neutralizations. Titration is a chemical technique we've used in the lab before, but we're going to talk about it in a little bit different way now that we know more about acids and bases. One of its primary purposes is to determine the concentration of an unknown acid or base. It's a process in which a solution of known concentration, so something we know its molarity, called a titrant, is dispensed from a burette to a known quantity of unknown solution, which is our analyte. We don't know what its pH is, we don't know what its concentration is, excuse me. And we're going to titrate them until the equivalence point is reached. The equivalence point is the point where all of the acid or base you started with is neutralized. A couple different indicators we've used, such as phenolphthalein or methyl red, are usually added to the analyte to show when the equivalence point has been reached. These are indicators that change colors at different pH ranges. So if the pH changes to a certain threshold, the color of the solution changes to match. In our lab, we've done it with that pink solution, phenolphthalein. It is clear as a base, but as soon as you add enough acid to it, sorry, I cut that backwards. It's clear as an acid, excuse me. As soon as you add enough base to it, it starts to turn pink. And at the equivalence point, the solution will turn just the lightest little pink, which lets you know that you've reached the end point of the titration. The progress of a titration reaction is monitored by a pH or titration curve. Okay, so here we are going to look at an example. And the reason we're doing this example, it's going to be kind of long, it's broken into 4 different parts here, is to see how our titration progresses as we add more and more of our base to it. So in our example here, we're starting with 50 milliliters of 0.2 molar nitric acid, HNO3, a strong acid. It's titrated with 0.1 molar sodium hydroxide. We want to calculate the pH of the HNO3 that we're titrating 4 different times. We want to know its initial pH, its pH after you add 20 milliliters, its pH after you add 100 milliliters, then its pH after you add 150 milliliters. So we're going to have 4 different parts here that I've broken into your notes into 4 different steps, and we're going to try to find the pH 4 different times. To get the pH, we need the H plus concentration. Okay? HNO3 is a strong acid. It's going to make our work a little easier. All right, let's go ahead and get started. I'm going to write down starting information we have here. We have 50 milliliters of our 0.2 molar nitric acid. Okay. We're going to add some 0.100 molar sodium hydroxide in stages to that and see how it affects the pH. But first, our initial pH. Okay, can't write. So before we add any NaOH, let's find our pH. This is a strong acid, which means when it reacts, my brain's turning off, it reacts to completion. It loses its proton and creates NO3 minus. What we care about is the H plus, because that's how you find pH. Since this is a strong acid, all 0.2 moles will turn into H plus. So we can find the pH is just the negative log of 0.2, which is 0.699. That is our starting pH of our acid here. Before anything else has been added to it, I have 0.2 molar H+, so I have 0.699 pH. As we add the base to it, it makes sense. This is our titrant here. As we add this, the pH should go up. It gets more basic along each step. All right, so our first actual thing here, so this was part A, we'll make this part B, is to add plus 20 milliliters of NaOH. Adding NaOH will neutralize some of our HNO3. Well, what we're going to need to do, we have molar, we have milliliters, all different. To be able to see exactly how much is neutralized, everything will be converted into moles. So I'm going to go ahead and take my acid I started with, convert that into moles. Molarity equals moles per liter. I have 50 milliliters, which is 0.05 liters. My moles of acid, multiply this, I get 0.01 moles of nitric acid. I'm going to do the same for my base. Its concentration is 0.1 molar. equals moles per liter. I'm adding 20 milliliters, which is 0.02. Multiply across 0.002 moles of NaOH. You have to convert everything to moles because when we're starting here, we have different concentrations to keep track of, different volumes. If I really want to see exactly how much acid and base I have, it has to be in moles so I can compare them. Okay, these two are going to react in a neutralization reaction. HNO3 will react with our base, NaOH. Okay. This Na doesn't really matter. It's going to just kind of be left off to the side. Same with this NO3. We don't care about that. The main thing going on here, you have an acid, you have a base, they're going to neutralize. The H, this is going to lose an H, it's going to go and make H2O. OH bonds with the H, and then you're left with these middle things. You can bond them together if you want. NaNO3. It doesn't really matter. That doesn't affect the reaction at all. That is a neutral salt. It doesn't change the pH. All we really care about are these two products. They're just going to, or these two reactants. They're just going to react with each other. We want to see how much is left. So we don't need this product or this product really for this reaction. So before we have HNO3, we have 0.01 moles of that. We have 0.002 moles of this. These two are going to react until one of them is consumed. This one will run out first. So it's going to lose 0.002. So will this. Not even going to bother with these products because they don't affect the pH. After, I have no NaOH left. It's all been neutralized, but some of this was consumed as well. I'm only left with 0.008 moles of HNO3. All right, so that's how many moles of acid I have left after they neutralize each other a bit. Let's find the pH. Don't just go plugging this number into the pH formula, though. This is moles. We need molarity. Molarity is moles per liter. Our moles is 0.008. Let's think about our liters. We started with 50 milliliters of this acid, but we just added 20 milliliters more to it. So we actually have 70 milliliters, which if we convert it to liters is 0.07 liters. Divide this and I get 0.114 molar HNO3. So that's the number we're going to plug into the pH formula. When you do, you get 0.943. Like we said, when we add the base, the pH will go up, but it hasn't gone up very much yet because I still have a lot of acid left. 80% of my acid's still there. So let's continue the titration. In part C, I'm going to add 100 milliliters. And we're kind of restarting from the beginning, not 100 more, but just now a total of 100 milliliters. So I add my 0.01 moles of nitric acid. Let's see how many moles of NaOH this is. It's 0.1 molar. It's 100 milliliters, or 0.1 liters. So I also have 0.01 moles of NaOH. Okay. Add my acid and base. Doesn't matter what my products are. So I had 0.01 of this, 0.01 of this. Well, I have equal amounts, so they're both going to neutralize each other completely. And I'm left with no acid, no base. pH is 7. Everything is completely neutral here. When you have the same amount of moles of acid and base, they cancel each other out, and you get a pH of 7. This point of the titration is called the equivalence point, which we're going to take notes on in just a minute. But the equivalence point is where the pH is neutral because you have the same amount of strong acid and strong base. The equivalence point also occurs when you're not titrating strong acid and strong base. If you have like a strong acid and a weak base, or vice versa, the pH won't quite be 7. But for strong acids and strong bases together, it always is. All right, so our last one here, the math for that one was nice. But what if I add even more NaOH? 150 milliliters. Which, if I do that molarity, I now have 0.15 moles. I left off a 0, but 0.015 moles. Which means I actually have more NaOH now than I do HNO3. Draw my reaction. I have 0.01, 0.015. They're going to neutralize each other, but actually this is the one that's going to be consumed and left with 0. My NaOH, I'm going to be left with 0.005 moles. So all I have this time is a little bit of NaOH left over. So 0.005 moles of NaOH, I want to calculate its molarity. It's moles per liter, so it's 0.005. My liters, I have 150 milliliters of this. I added it to 50 milliliters. The number's not here, but I started with 50 milliliters of this, so it's going to be over 0.2 for 200 milliliters, which means my answer is going to be 0.025 molar NaOH. To find the pH of that, it is a strong base. I can find the pOH. It's the negative log of that concentration. The pOH equals 1.602, which means the pH, if I subtract that from 14, it's just 12.4. pH has spiked a lot at this point. So the pH went from really low to 7 to 12.4. pH curve will look something like this. This is the same problem here, but I plotted the pH curve so you can see what the pHs are at all times. So I have my HNO3, my nitric acid, in my beaker, and I start adding NaOH, and you'll notice for the first bit here, not much changes. The pH goes up slightly and slightly and slightly until the moles start to be equal to each other. And the pH is going to shoot up. And at this point is where the moles are exactly equal. The equivalence point, pH is 7. Adding just a few more drops is going to make the pH spike up even more, and then eventually start to taper off towards my NaOH. The most important thing here is the equivalence point is the point where the enough titrant has been added to exactly react with your solution. The titration curve of a strong acid and strong base will always have this nice symmetric shape. The equivalence point will be at 7, and you can also titrate weak acids and weak bases, but the curves will look a little bit different. All right, so this is going to be our last example problem, basically the end of the notes, but it is similar to the last problem. It will take a good bit of time. When you do a weak acid with a strong base, or a strong base with a weak acid, and you're mixing a weak and a strong, it won't work out quite as nicely. So the first thing we're going to do is, just like last time, a stoichiometry problem. You're going to figure out how much acid or base you have left. But the problem with this one is you're going to have some weak acid or weak base left over. So when you go to find its pH, you can't just simply find its pH, assuming it's a strong acid or base that fully dissociates. You have to do an equilibrium problem using the Ka to calculate pH. So it's basically the exact same as the last one, adding that extra step at the end. So here's our problem. It's going to be pretty much identical to the last one, but I'm starting, the main difference, I have a different acid, and this is a weak acid. 50 milliliters of my 0.1 molar weak acid titrated with 0.1 molars of NaOH, my strong base. I'm going to calculate the pH of this solution initially. After 25, 50, and 60 milliliters of NaOH, the Ka of my weak acid is given to me. Okay, let's do it. Starting with initial. I want to know the pH initially. Well, I haven't added any acid yet, so what I'm starting with is 0.1 molar acetic acid. I know its Ka is 1.8 times 10 to the minus 5. I'm going to find its pH. So this is just like last chapter. My acid is going to dissociate into H plus and C2H3O2 minus. I'm going to set up my ice table, my 0.1, my 0, my 0. The reaction is going to go to the right, so I'm going to subtract this, plus X, X, and X. If I solve for X, I know my H plus concentration, therefore I know my pH. Ka is 1.8 times 10 to the minus 5. It's products over reactants, so it's X times X over 0.1 minus X. I'm going to use the rule where I can get rid of this minus X. Now solve for X. Uh, 0.00134. That's my concentration of H plus. If I take the negative log of this, my pH is 2.87. So this is just like Unit 14, solving for the pH of a weak acid. Okay, we haven't added anything, we haven't done anything new for titration yet. Well, we will in Part B. Part B, I'm going to add 25 milliliters of 0.1 molar NaOH. This base is going to react with this weak acid. Okay, plus NaOH. When these things react, they're going to neutralize, basically. This time, though, the products matter. One of my products will be C2H3O2 minus. The other one is just water. There's also an Na plus floating around, but nobody cares. Also, nobody cares about water. This is the only one that really matters. This is your conjugate base. So this makes a bit of a buffer solution here. So before any reaction happens, I had 0.1 mole of this. I had, well, let's calculate how many moles of NaOH I have. 0.1 equals moles over 0.025. Okay, so I have 0.0025 moles of this. Jump the gun on this one a little bit. I also need to calculate my moles of HC2H3O2. I have 0.1 molar, but I only have 50 milliliters of it. Which means I have 0.0050 moles of acetic acid. And at this point, nothing over here. These two things are going to neutralize each other. I'm going to run out of NaOH first. It's my limiting reactant. But it's going to neutralize a good bit of the acetic acid on its way out. When this gets neutralized, it's going to make more of this. After this reaction, I'm going to have 0.0025 moles of this, 0 moles of this, and 0.0025 moles of this. All right, so I have no acid left over, but now I have a buffer being made here. I have equal amounts of this and this. We're going to calculate the pH of this buffer real quick. We're going to take these moles, 0.025 moles, and turn it into molarity by dividing by my total liters. 25 plus 50 that I started with. Okay. .033 molar. And that's just the number for both of these. I was just being lazy and just did it once. pH equals pKa plus the log of base over acid. I have the same number, but this is the one that goes on top. 0.033, because that's its molarity, divided by 0.033. pKa is the negative log of a Ka given to me in the problem, plus the log of 1 is just 0. So the pH of this one equals this, which is 4.74. That same number we keep seeing. So in part B, the pH equals 4.74. What's special about this reaction, exactly 1/2 of my starting weak acid has been neutralized. A name for this often is called the half equivalence point. Exactly half of it has been neutralized. What's special about this is that this is the place where my acid and base have the same concentration. Therefore, this whole part of the reaction doesn't really matter, and the pH just equals the pKa of the acid. So if you want to find the pKa of a weak acid, this is the way to do it. You titrate with just enough of your base to neutralize half of your acid, and then the pH that you calculate will just be the pKa of that acid. So that one's a little special. Part C, I'm going to add 50 milliliters of NaOH. So we're going to again count how many moles that is. So I still have 0.1 molar. So this is 0.005 moles of NaOH I have now, which is the same as my starting amount of my acid. So we're going to write out our reaction. The only product that really matters is this one, so that's the only one I'm going to write. So I start with 0.005 of this, 0.005 of this, 0 of this. If you care, I have 0 H2O, 0 Na+. They don't change anything. All right. So these two are going to react and completely neutralize each other. So I have 0 and 0. But this isn't going to be a pH of 7 like last time, because now I have some of this left over. I have 0.005 moles of my conjugate base, which means this solution's a little bit basic. It's not a pH of 7. The pH is whatever the pH is of this leftover base. So let's look at it. This base will react with water, and it'll gain an H+, and leave a little bit of OH-. Well, it's Kb we don't know, but we know the Ka of the acid is 1.8 times 10 to the minus 5. So we can use the idea that these are conjugate acid-base pairs to find the Kb of this reaction, which we need because that's what we have over here to start. That's what's dissociating. So Ka times Kb equals 1 times 10 to the minus 14th. Plug in my Ka. Find Kb. Okay, I'm going to set up my ice table. I need my initial concentration of this, which I don't have yet. All I have is moles. So again, I did take this moles and turn it into molarity by dividing by how many liters of solution I have. I added 50 more milliliters, and I started with 50 milliliters, so I have 0.1 liters. Divide this by 0.1, I have 0.05 molar acetic acid, acetate ion. That's what I'm starting with here. None of this, none of this. Minus X plus X. Okay, now we're just finding the pH like we did in part A. Kb is 5.56 times 10 to the minus 10 is x squared over 0.05 minus x. Get rid of the minus x part. Solve this for x. We get 5.27 times 10 to the minus 6. That equals x, which is our OH minus concentration. So I can find the POH by taking the negative log of that number. And I get that number. Find the pH by subtracting 14, that from 14. And I get 8.72 as my answer. All right, trying to get through these problems as good as I can. We definitely will do some of these in class as well. So in this situation, kind of summarizing everything that happened, I added enough NaOH to completely neutralize my acid. So I was left with none of those things. But I created some acetate ion in the process. So I have to find the pH of this. This is going to dissociate into some OH minus. We calculated that to be this much OH minus, so we can find the POH of this solution, letting us find the pH. So this is the equivalence point where my acid and base equal, but it's actually slightly basic because the strong base is a little bit stronger than the weak acid. It's going to increase the pH. And our very last step, which you might think might be the worst, but it's actually the easiest one. All right, I have 60 milliliters of NaOH, which I'm going to do the molarity real quick. Molarity is moles per liter. 0.1 molar equals moles over 0.06 liters, 0.006 moles of NaOH. Same reaction, it's going to react with my acetic acid. When this reacts, I only had 0.05 of this. Is that true? My brain turning off? Probably. Yeah. Now I actually have more NaOH than my starting acetic acid. So when these neutralize, I'm going to be left with a little bit of NaOH. And a little bit of my acetic acid as well. So I actually have two bases in solution here. What's great about this, the strong base is going to be like 99% where the OH minuses come from. So this hardly contributes. We'll just don't even worry about that part. Technically, you can calculate them both, add the OH minuses together, but this is going to be where most of them come from. 0.001 moles of NaOH. My total concentration now is 60 milliliters and 50, so I have 0.110 liters. Divide that, I get 0.00909 molar. Okay. NaOH. So the POH of that, if I take the negative log, is 2.04. pH 11.96. And that's it. That's how the pH changes at each of those 4 steps. Okay. That's probably the last math problem. I know there's a lot. All right, if you have a strong base with a weak acid, this is what the titration curve will look like. The pH will be greater than 7 at the equivalence point. Opposite, if you take a weak base, neutralize it with a strong acid, the pH will be under 7. It will be slightly acidic at the equivalence point. All right. Last thing here is just a quick little blip about indicators. Indicators are those things like phenolphthalein and methyl orange or red or whatever that help you in a titration. There's 2 ways to determine the equivalence point. The first is more accurate. Using a pH meter, you can graph the titration curve and manually find the equivalence point. But we usually use an acid-base indicator, which is a chemical that turns colors when the pH changes. When the pH or when the indicator changes color, that marks that the endpoint of the titration has been reached. The equivalence point of a titration, defined by stoichiometry, is not necessarily the same as the endpoints. The equivalence point is kind of like the true endpoints, where the moles of one equals the moles of other if everything went perfect and all your math was exactly right. And then the endpoint is actually going to be a little bit after that when the indicator changes color. So the endpoint is actually usually a little bit past the equivalent point. Carefully choose which indicator to ensure that error is negligible. Indicators are just weak acids that change color depending on whether or not they have their protons. There's some math we could go into with this Ka and stuff like that. It's not super important. You should just kind of know an indicator is something that changes color when the pH changes. The reason the pH changes is because it has a proton at a certain pH and doesn't have a proton at a different pH. When we choose an indicator for our titration, we want the indicator endpoints where the color changes and the titration equivalence point to be as close as possible. The dramatic change in pH near the equivalence point makes it easier to choose an indicator because the color changes will be sharp, usually occurring by the addition of a single drop of titrant. When you do a titration, if you add just a slight too much amounts of acid or base, your pH is going to be very different. You're working on a very fine balance there. Okay. That's a lot. That's a lot of math. We're going to talk about this in class. We're going to do examples of buffers and titrations. There's some of the harder math problems applying to concepts that we do throughout the entire year, right? But also one of the most important. Titrations are asked most years on FRQ questions. Buffers are asked every year in a variety of ways. We're going to practice these in class, right? Hopefully at least some of that made sense. Okay? All right. Have a good day, everybody.